some 30 seconds and you can start now. I think the recording is already started. So Frank, please start. Frank, you are muted.
Okay. Thank you very much, Arsh, for reminding me this, and also for the nice introduction. So it's great to present, to be able to present my talk to this conference. I would have loved to actually have such a conference in person, because this is, of course, leads to much more ideas and discussions. But I hope that we will be able to kind of go back to normal things soon. But anyway, I will talk about frustrated systems, reduced density matrices, residual entropies, and non-local symmetries. And actually, I decided to change my talk a little bit in the light of the Nobel Prize of this week, namely, especially somehow the Nobel Prize, the half of the Nobel Prize that was awarded to Parisi. And the prize motivation was really for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. And out of this whole discussion of the Nobel Prize committee, of the Nobel Prize in Physics, there was a central kind of topic about frustration, and actually spins that frustrate on a triangular lattice. So if you have like an antiferromagnetic Ising model, that indeed this leads to frustration, and that this actually gives rise to lots of interesting emerging phenomena. That somehow the local microscopic frustration actually leads to very non-trivial global kind of feature. And this is, of course, something that we physicists are very much interested in. And I would like to kind of give you some idea of how problems like that can be treated using the methods that come out of this quantum information theory, namely this way of looking at of many body systems from the point of view of entanglement, and also like trying to understand how these non-local properties can actually understood in terms of non-local symmetries, kind of emerging symmetries that are responsible for the critical behavior. So brief outline of my talk. So I will first start with some notion of convex sets of marginals and reduced density matrices of classical StatMech models. Actually, this is something that certainly David Mattiotti is, of course, one of the world authorities in. But it turns out that actually these very, very similar notions are very valuable in understanding classical statistical mechanical problems that have to do with frustration. And at the end, the more somehow I got into understanding classical StatMech, and especially frustrated systems, the more I realized that actually this problem is very, very similar to the quantum problem of simulating quantum spin chains or lattice systems. So turns out that the full richness of these problems, or also the fact that you have this exponential phase space and this exponential wall, is very, very similar for classical statistical mechanical problems and quantum problems. And I will actually in this talk focus on the StatMech version, although somehow many of the things also go through for the quantum case. And I will end my talk with trying to give you some ideas or some flavor of how these very nice emerging behaviors can be understood in a local way if you kind of look at this from the point of view of these tensor networks, and you get something like a very advanced mathematics that allows you to develop or to combine notions, very, very deep notions in quantum field theory, to actually very mundane notions that occur already in very simple frustrated systems. Anyway, so let me start with a very general introduction about this complex behavior that certainly was the reason that Parisi got this Nobel Prize. So it's really about emerging behavior and critical system, and somehow what is fascinating is that such behavior arises whenever you have something like a competition between different forces or between different quantities. And of course, we are all familiar with this big battle of entropy and energy and statistical mechanics. Now, if you have something like an Ising model, you want to minimize the energy while you want to point out all the spins in the same direction. If you have an Ising ferromagnet, of course, but the entropy would like to kind of be completely disordered. So you would like to be the spins to be completely disordered, and it's clear that this temperature is kind of controlling the weight you associate to these two behaviors. And the fascinating thing is that in between that there is something like a phase transition between the two extremes, in which and energy takes over everything, or entropy takes over everything. And in the middle, there is like a phase transition. And that's exactly what gives rise to this criticality. But this is not the only path to complex behavior. There's also, like at zero temperature, there's this whole kind of wealth of frustrated systems. Like if you take Ising antiferromagnets on a triangular lattice, you take a big triangular lattice, and on every kind of these triangles, you have some notion of frustration. And it turns out that this frustration is also giving rise to non-trivial emerging behavior, to kind of power law decay of correlations, to all these kind of things. And you would like to understand and simulate this. A third way that is also kind of giving rise to very, very similar physics, although all these three setups are very different, but deep in themselves, actually all three kind of the emerging behavior from these three different cases will turn out to have the same origin, is actually by not working with classical statistical mechanics, but starting to use quantum Hamiltonians that have like non-commuting terms. And this is exactly the frustration in a quantum mechanical problem. So you're all aware that of course you have like typically your kinetic energy terms and your potential energy terms. Well, these don't commute. And of course the whole complexity and the whole richness of the quantum many-body problem is exactly the fact that you have like different non-commuting terms, and that you have something like this frustration that emerges out of this. So this is an example of a three-spin system that with the Heisenberg Hamiltonian. And the question is, what is basically the ground state of that model? Well, you basically have this monogamy of entanglement. You would like to have singlets between all nearest neighbors, but that's impossible. And therefore, somehow the system starts to arranging itself in a non-trivial configuration, actually, in this kind of configuration in which you share a little bit entanglement with the left, a bit entanglement with the right. And that's basically how, if you don't do this on a much bigger scale, how the critical behavior, the phase transition or the second order phase transitions in your system at some point will kind of emerge by these competitions that you have there. Now, what is very nice and what I like very much is that actually this whole behavior, or this whole kind of the phase diagrams of such systems, and especially such statistical mechanical systems, can be very nicely understood in terms of marginals, and in terms of somehow reduced density matrices. So what you effectively do here in this plot, I look at a little bit at a model that is a little bit more complicated than the Ising model. I look at something that is called the Potts model, the Q-state Potts model on the square lattice. So the Potts model is, instead of having like only a two-level system, you have something like a three-level system. And using this three-level system, you're able to to basically trying to understand the phase diagram as a function of the temperature, as a function of somehow the couplings in your system. So the systems, the spins would try to be aligned somehow with if this J is positive, and you have some magnetic field. And then you're trying to understand, okay, like for this type of Hamiltonian, what are the possible behaviors? What are the possible values of my magnetization, of my energy kind of expectation value, or from my entropy density? So this S is basically the density of entropies. And you plot all these three quantities with respect to each other for any possible probability distribution, because of course we are talking about statistical mechanics here. So the whole system is basically governed by a probability distribution. And you basically, for any probability distribution, you plot somehow these three quantities, the ordered parameter, the magnetization, the energy density, the entropy density, and you see that actually all the possible probabilities, these marginals, lie in some nice convex sets. And the extreme points, there are singular points on these convex sets, like for example this point A, which is exactly the second order phase transition of the three-state Potts model. It happens that actually at some critical point there is something very non-trivial, something dramatic going on with this behavior, and indeed you can completely see this by looking at the marginals of these reduced density matrices. And then you get here your second order phase transition. But there's two other very interesting kind of regions here. For example, this region B here, this whole phase on top of it, is actually some kind of a very nice competition between somehow this H and this J. And what it gives rise to is some system that resembles this so-called hard square problem. The hard square problem is that if you have a spin up, then all the spins around it have to be spin down. And if you start calculating this, you see that indeed this is a very much frustrated system, and you have some non-trivial entropy density even at zero temperature. And this is actually exactly the physics that gives rise to somehow this critical behavior. And there's another one of these singular planes in your system, and this is, for example, this period C, and this is even a different kind of way of getting frustrated systems. This is the so-called square ice problem, and in which somehow all this is a very famous problem that is inspired by the ice problem that Pauling kind of introduced, and it's basically a two-dimensional version of it, and it also gives rise to some non-trivial residual entropy of ice. So then you can start looking at these convex sets for different values of Q. So instead of having a 3-state model, you have a 5-state model, and you see that actually something changes. Instead of having this singular point here, you get some new singular plane here in this kind of point A. And this exactly points out that this is actually a first-order phase transition instead of a second-order phase transition. So basically the whole world of the phase diagram can be completely read off somehow these convex sets. And these are really the complete analogs of these famous kind of reduced density matrices that people in condensed matter, quantum chemistry have been using, and especially also David. So there's of course quantum versions of that are very similar. So instead of kind of basically the entropy, so you see here I have something like this energy and the magnetization, and then I have this entropy, which plays the role of the non-commuting parameter, the competition. If you kind of go to the quantum case and you start plotting similar convex sets, what you have here is of course something like the energy term, the magnetization in that term, but then you have this non-commuting term, and this plays the role of entropy. And you can start making convex sets for all these things, read off somehow where the phase transitions are, the second order phase transitions. Can actually, this is for example a plot where we do this for a model that resembles like Bose-Einstein condensation. So basically you take the Laplacian, the expectation value of the Laplacian, you kind of take the entropy density, you take the order parameter, and you see that actually the second order phase transition, the Bose-Einstein condensation, can be completely understood in terms of these convex sets. Okay, but what I would like to do in this talk is basically focus on these very interesting kind of non-trivial behaviors that you get when you have a simple spin system like that. But nevertheless, you have this like emerging behavior, this emergent critical kind of behavior on these planes. So you have these frustrated systems that emerge there. Okay, so basically what these residual entropy problems are about is about counting. It's basically about calculating or counting problems on the lattice. And the most famous of these problems are these dimer problems. Okay, so you have something like a square lattice or a cubic lattice, and you could put a dimer on every kind of between any two neighboring vertices. But if there is a dimer there, you cannot have any other dimer touching any of these kind of vertices. So every vertex can only be kind of combined, can only kind of touch one other vertex via a dimer. And the whole kind of notion of these entropies, or the fact that will give rise to this critical behavior, is the fact that you have many possible kind of configurations, but these possible configurations have very non-local effects. So if I have a dimer here, this will affect actually all the dimers even far away, even if there's exponentially many kind of contributions to this. And these are very hard problems, very interesting problems to deal with, and trying to understand basically what is going on, what is somehow, how do you do these counting problems. Okay? And this is actually, from the physics point of view, this has very interesting connections with gauge theories, with integrability, and so further. A problem that is probably more famous for people in quantum chemistry is certainly the ice problem. Okay? So the ice problem in 3 dimensions. So you have something like a pyrochlore lattice, and you have your kind of H2O kind of molecules, and then you on every vertex, of course, you have basically your oxygen, and then you have 2 hydrogen atoms next to it, and then you want to understand how many kind of ways can I put these hydrogen atoms on this pyrochlore lattice such that no 2 hydrogen atoms are close to each other. So again, this is a very similar kind of counting problem as these dimer problems, and this is this famous problem that Pauling kind of realized. Pauling realized that indeed the residual entropy at ice, the fact that you basically have a violation of the 3rd law of thermodynamics, that actually they can still have entropy at temperature 0, is exactly because of the fact that there's many kind of exponentially many configurations that satisfy this ice rule. But it's not because somehow you know that there's exponentially many of these satisfying the ice rule, that it's an easy problem to count how many kind of configurations satisfy this, and this is exactly somehow the problem of calculating the ice. So there's many other kind of problems also that arise in very natural ways, like the hard square problem. Take, for example, a matrix, and on every matrix, if I have a 1, it has to be surrounded by zeros. Okay, this is a famous problem, and you would like to know how many matrices are there of that kind if this size of this matrix becomes very large. This is the famous hard square problem that actually also, well, is very similar in spirit to all these frustrated systems. And what all these these systems have in common actually is that this frustration, exactly somehow this is exactly why the Nobel Prize of Paris was exactly about this. Now that is frustrating, this very simple frustration gives rise to very non-local and very interesting global behaviors, and that's actually where we want to work towards in this talk. Okay, so what is the problem with these counting problems? That of course, in principle, these are very hard problems, and so counting problems are, even in principle, is sharply hard. So we talked about this in the discussion section. Okay, there's this hardest cases and there's this kind of complexity theory. Well, in principle, these problems are kind of sharply hard. But of course, if you have lots of symmetry and translation variance, it turns out that actually these notions of complexity theory actually become a little bit irrelevant, and it's actually more possible to make progress. But nevertheless, there have been lots of efforts to calculate these entropies and things like that, especially using Monte Carlo sampling IDs. And it turns out to be very hard because Monte Carlo methods are very easy or very well suited for calculating relative quantities, but not for absolute quantities. And what I want to convince you also in the first part of this paper is that indeed these tensor networks, this DMRG type of methods, actually allow you to calculate these entropies in a very straightforward way. So to do this, let's start with a very, very simple, this hard square constant. So I have basically the one-dimensional hard square problem, which is if I have a 1, it has to be surrounded by zeros. And the question is, how many strings can I write down of that kind? Okay, whenever I have a 1, it has to be surrounded by zeros. How many strings of that kind can I write down? This is, of course, well, for people, I'm sure that most of you know that, of course, somehow this is related to the Fibonacci numbers and all these kind of things. Well, how do you kind of prove this, or how do you understand this? Well, you actually solve this problem exactly using the transfer matrix approach. Okay, so basically what you do is construct a tensor network. So there have been talks on DMRG in the previous talks of this conference. So basically you write down a trivial one-dimensional tensor network where somehow these nodes here, this is just if this is a 0, this is a 0, this is a 1, this is a 1. So basically this is just this node or this line is basically multiply that column with this somehow row. And you can immediately convince yourself that the product of all these matrices will exactly give you somehow the total number of configurations of that kind, because it tells you if there's a 1 somehow here and a 1 there, this is not allowed because I need to have a 1 and a 0. So the only configurations that are possible are 0, 0, 0, 1, 1, 0, and 1, 1. And this is the 0, 0, the 0, 1, the 1, 0, and the 1, 1. You're not allowed to have the 1, 1, the other ones you have. So basically the total number of configurations is the product of all these matrices. Therefore, you basically take, for example, periodic boundary conditions, you have to take the trace of that matrix to the power L. Of course, how you do this, you basically diagonalize that matrix, and the eigenvalues are 1 plus square root of 5 divided by 2, 1 minus square root of 5 divided by 2, take this to the power L. Well, this is exactly somehow the hard square constants for this one-dimensional case. And of course, this is completely trivial, this is an exact result, but what we will do is very similar for the higher dimensional problems, which are very much harder. They are in principle exponential problems. So what is going on here? Well, how do you calculate somehow this residual entropy of this hard square or the hard square constant? Well, you basically write down a two-dimensional tensor version of this one-dimensional problem, in which somehow here this is basically the spin. If this spin is up, well, then somehow if this is a 0 spin, well, then this can be 0 or 1. But if this is a 1 spin, this has to be a 0. Well, you basically write down somehow this index, this tensor is this index is equal to this index equal to this, so there's 0, 0, 0, 0, or 1, 1, 1, 1. And you just can immediately convince yourself that the contraction of that tensor network will exactly give me basically the residual, the entropy, somehow the total number of configurations that satisfy the hard square constant. So what did we do in the 0D case? We basically went to the transfer matrix approach, but you do exactly the same here. So basically, if you kind of look at one of these big rows, these infinite rows, you basically repeat these rows infinitely many times after each other. And therefore, the residual entropy of that model will nothing be more than the leading eigenvalue of this problem. In this problem, what you see is that whenever I have a 1, it has to be surrounded by zeros. Turns out that this is actually completely equivalent to kind of diagonalizing or finding the ground state of a quantum system with Fibonacci onions. Okay? There's some kind of a non-trivial frustrated kind of condition that somehow if this is a 1, it has to be surrounded by zeros. And of course, because it's basically equivalent to finding ground states of quantum Hamiltonians, you can actually use this DMRG methods or variational matrix product state methods for finding these leading eigenvectors of these models. So basically, you try to find a matrix product state such that if you multiply it with this transfer matrix, you get something proportional to somehow that same matrix product state. And this lambda would be the entropy density for this system. So how does this work in practice? Well, you basically make use of all the tricks that people have been using and developing in the field of matrix product states in terms of DMRG. So this is basically something like the state-of-the-art methods, or like tangent space methods, and is related to the time-dependent variational principle, very similar to what Dirac actually derived for Hartree-Fock states, but now applied to the manifold of matrix product states. So actually all DMRG methods can in some sense now be understood in this language of manifolds and tangent spaces and time-dependent variational principles. And using this, you can actually find this leading eigenvalue, and you do this calculation. And actually, for the square ice, this led to kind of, I have to agree, it's kind of ridiculous, but nevertheless, we were able to kind of calculate the free energy of this hard square model, or the residual entropy, up to somehow, I think this was like 60 digits. Okay, so 58 digits of precision, which is, of course, like, it just shows you that actually these matrix product state methods, they are like pretty kind of strong. So they allow you to calculate that residual entropy of ice density with 58 digits of precision without actually too much effort. This is like the bond dimension is like 80 in this case. And there's lots of other kind of things that you can do. So of course, once we did this, we wanted to kind of start looking at more challenging problems, like what happens if you kind of go to higher dimensions. So what happens if you really kind of look to 3D frustrated systems? Really, is there a way for calculating things like the residual entropy of ice? Really the problem that Pauling originally kind of devised and understood, that actually the residual entropy of ice, or the zero temperature entropy of ice, is actually has its origin in this combinatorial problem. So you can actually phrase that problem of entropy of ice in a very similar way, and a very similar vein. So you basically write down a tensor network that corresponds to the Python lattice. It's basically these tensors again have all zeros and ones depending on what is allowed. You can write down a transfer matrix for this, but this transfer matrix, instead of a 1D transfer matrix, is now a 2-dimensional transfer matrix. Okay, so basically this is how this tensor network kind of looks like. It's the tensors only have ones and zeros depending on somehow the configurations. And now basically the residual entropy of ice will be kind of correspond to the leading eigenvector of that transfer matrix. Turns out that there's like hexagonal eyes and diamond eyes and all this, and using these transfer matrix approaches, you can actually prove that they will have exactly the same residual entropy because of symmetries and things like that, which is, I don't think this was actually known. But anyway, so then there's this kind of this whole arsenal of methods using kind of PEPS methods that was started somehow in some collaboration with Ignacio Sirac and myself, where we kind of started looking at problems like finding eigenvectors of such systems using the generalization to higher dimensions of these matrix product states, and you start trying to understand basically how do I kind of optimize this, and you can actually do this. It is not so easy, and it's much more work than the usual DMRG, but you can actually do this. And using these methods, we were able to calculate somehow this residual entropy of ice up to something like 5 or 6 digits of precision, which is more than basically any other of the Monte Carlo methods, because in Monte Carlo, again, it's very difficult to get these absolute values, and the only way of basically calculating entropies is by starting from infinite temperature and then basically integrating the specific heat. So here, using these tensor networks, we can immediately target somehow the zero temperature case and just calculate somehow the eigenvalues of that transfer matrix. And well, this is like the bond dimension that we use. This is very low in comparison with matrix product state, but nevertheless, this was more than enough to see that somehow you have like 5 digits of precision of convergence. So this is still the best kind of state-of-the-art way of doing this. Now, what is interesting is that you look at this kind of problem of spin ice, or this ice problem of Pauling, and you start looking at now correlation functions, and you see that effectively all these correlation functions are decaying like a power law. So it feels that indeed this frustration has been leading to somehow very long-range physics, to somehow power law decay of correlations. And this is fascinating. No? You have very simple rules. You have this very local simple rules, but the fact that somehow you have to satisfy these local rules enforces that you kind of get emerging long-range physics that somehow has power law decay of correlations, has non-trivial exponents, critical exponents, and so further. And this is exactly the kind of things that we would like to understand. So you can actually do the same thing for these dimer coverings that we talked about, that I talked about in the beginning of this talk. So like what happens if I have dimers and I would like to do the counting of the dimers. It turns out that actually for the 2D case, so you would like to count how many kind of dimers can I put on a square lattice when I start the counting. These are these very famous paper of Castellijn Fortuyn and then also Fisher and Leap, in which they actually calculate this entropy exactly and or the entropy density exactly. And this is using basically by mapping this to a free fermion system and then calculating this entropy. And indeed, you can reproduce these things to an extremely good precision using somehow this black box matrix product state methods. And the same thing happens in 3 dimensions. If you would like to kind of calculate somehow the residual entropy, the total number of dimer configuration on a 3D lattice, turns out to be very hard to do this with Monte Carlo. Actually using somehow these PEPS methods, it is pretty straightforward, and you can actually get somehow these numbers out that calculate or that give you somehow the entropy density. And again, what happens here is that, just as in the previous case, you get again critical behavior. So you get basically power law behavior of correlations in these systems. And actually this can be understood in terms of Coulomb phases. And of course, the reason that you get these long range features is actually that there's some hidden U1 symmetries in these systems. Okay, there's actually many more systems that you can write down like this. A very famous one is actually like the anti-ferromagnetic Ising model, where you kind of do this on a frustrated lattice, for example, on the Kagome lattices or on triangular lattices. And it turns out that actually this, if we kind of use these methods that we have developed and that I was explaining you before, and you try to apply this to somehow frustrated systems like the anti-ferromagnetic Ising on a triangular lattice, turns out that these methods completely fail. Okay, and to us, this was actually very interesting, because this meant that there's something like a sign problem in Monte Carlo, or a sampling problem in spin glasses, even for somehow these DMRG methods. And this is something that that was not really expected. And indeed, somehow this was something that puzzled us for quite some while. How can we circumvent this, and how do we have to deal with this? So, because actually the normal standard actually DMRG or matrix product state methods don't work for these really kind of frustrated systems like that. And then somehow I had a very good student, Bram van Ecke, together with Colbois from APFL, and they basically then solved this problem by understanding that before you have to use these matrix product state methods, you actually have to start renormalizing spins. And by renormalizing spins in a black box way, and you can use this using linear programming techniques, you can actually map these frustrated problems to actually non-frustrated problems, for which these MPS techniques then completely work. And somehow
Frank, 5 minutes. Frank, 5 minutes to go.
Only 5 minutes, but I thought it was 40 minutes. Okay. But anyway,
we should leave some questions. Maybe you have extra minutes as well. Okay, I will let.
No, it's okay. It's okay. I will speed up. But anyway, so you can do this and start looking at these problems on Kagome lattices, where you have these are actually experimental systems that are of interest, and then you start seeing that indeed these renormalized spins start effectively, even on Kagome, start behaving like exact Ising spins, and you can actually start calculating the residual entropy for these experimentally relevant quantities. And you see that basically also these systems have these critical behaviors, have these long-range correlations. Yeah, this is exactly in this last 5 minutes of my talk. I would like to kind of give you a bird's eye view on how these emerging symmetries, or somehow how this critical behavior, how this can be understood in terms of these tensor networks, how actually these tensor networks allow you to see that there will be some non-trivial long-range physics emerging there. And I have to apologize, it will be pretty formal from here on. It will kind of involve non-trivial mathematics, but nevertheless, you have to kind of understand that all of this is at the end just some, from the point of view of tensor networks, this is all very natural. These are all very simple linear algebra kind of operations. They're all kind of so basically what we will have to do is the representation theory of category theories, of fusion categories, which is like an extremely abstract kind of branch in mathematics. And it turns out that looking for these symmetries in these frustrated systems has allowed us to understand somehow these non-local symmetries in terms of very simple objects. And these simple objects are actually themselves also matrix product operators. So indeed, so how does that manifest itself locally? So this is the whole kind of beautiful feature of representing somehow frustrated systems using tensor networks, is that you have like local descriptions of your complete full kind of methods. So you have somehow these local descriptions, and it turns out that all these methods, all these models that are critical, actually have in some sense a very non-trivial, non-local symmetry that is emerging. And this emerging symmetry is exactly the one that is responsible for somehow the critical behaviors. So what happens is that these tensor networks, they have somehow, there are something that are called matrix product operators. So these are objects that you put on these virtual links, these kind of links that connect these different tensors to each other. And these local links, these are lines, these are something like Wilson loops for people that are familiar with high energy physics, that can be pulled through the lattice, that are kind of invisible. They are like symmetries, like you have a link, you have a matrix product operator that lies here, and you can pull it through this lattice side, and this thing kind of can be completely pulled through the lattice. So this is a non-local symmetry, because actually the way somehow you have to kind of, this object here is correlated to this, is correlated to this. So it's a very non-local, information that has to be kind of conveyed to be able to see this as a symmetry. So it's a very non-local symmetry that actually will give rise to global topological features. And these topological features are exactly the ones that are responsible for the criticality in these systems. Okay, so how does this actually work? Well, indeed, so you have all these tensors, and these tensors of all these frustrated systems that we have been talking about have some non-trivial symmetry. So it means that there is actually a matrix product operator, in this particular case, this red thing, that can be pulled through these objects. So typically we can, of course, decompose any lattice in terms of trivalent kind of, or any tensor in terms of products of trivalent kind of tensors. And these tensors, these trivalent tensors all have some non-trivial property. And it turns out that these red lines, these objects, these tensors, they are formalized, or they are representing matrix product operator algebras. And it turns out that there's a very kind of active program in trying to understand and study them, because they give basically local manifestations of the global topological properties in these systems, and they connect very exotic kind of areas in physics, like category theory and mathematics, also string nets, topological field theory, conformal field theory, integrability. There's many notions where somehow that can be understood using such non-local symmetries. And all these examples of critical stat mech models that people kind of actually construct and study, and also kind of integral models, turns out that they can all be used or constructed using somehow this matrix product algebraic framework. Okay, and this is through somehow something that is called the strange correlator approach. So basically, what this is about is that you start from a featureless quantum many-body system that actually has some non-trivial topological order, and then you project that this is a two-dimensional quantum wave function, but you take the overlap of that wave function with the product state. So basically, you project out all your spins, and this is basically the interface between some theory that is basically has zero correlation length but has global topological order, with another theory that has a zero correlation length but has no topological order. And this is in some sense the interface between two competing theories. And this interface, on such an interface, you expect indeed something exotic going on. And this is exactly somehow the critical kind of behavior can be understood in such kind of a field theoretic way. Okay, so like to go back to this anti-ferromagnetic Ising model on the triangular lattice, you basically start from something that is called a string net. It's like a string net that was constructed for topological field theories, and it's really some state that has zero correlation length. It's a two-dimensional quantum many-body wave function that has a zero correlation length but has topological order, and this topological order is manifested by the fact that there's such a matrix product operator symmetry. You project out all the spins on a physical level. This gives rise to a statistical mechanical model of two dimensions that has exactly the same matrix product operator symmetry, and that's the one that is actually giving rise to the critical behavior of somehow your correlation functions in your big system. Okay, so in the last kind of 2 minutes, let me try to kind of go a little bit more into the mathematics, so you can actually characterize all these matrix product operator symmetries and make use of some theorems. So this is actually the really great thing, I would say, of this tensor network or this DMRG type of approaches to condensed matter physics, is that there's not just somehow the computational component. There is actually also a very nice theoretical component in which somehow you can understand somehow the emerging behavior. You can understand that indeed there are non-local symmetries, that there's non-local entanglement present in these systems by studying the symmetries of these tensor networks. And for a review on that, we just kind of will just publish, I think somewhere in the next weeks in the Reviews of Modern Physics, a paper together with Ignacio Chirac, David Perez Garcia, and Norbert Schuch, where we basically explain all these kind of theoretical aspects of tensor networks, how they give rise to somehow possible classifications of the different phases of matter and topological phases of matter, and actually also critical behaviors. And this kind of matrix product operator symmetries play a very kind of central role in this. Okay, so what is actually going on? This general formalism is about basically constructing tensor networks with non-trivial symmetries. So when you have symmetries like that, actually you can then multiply two of these symmetries with each other. They also have to be a symmetry, and this means that there's some kind of a notion of an algebra of these symmetries. It doesn't have to be a group, it can be a general algebra. This algebra kind of satisfies some associativity conditions. And actually, there's lots of algebraic conditions that these things have to satisfy. And it turns out, and this was also a big surprise to us, that actually at the end, all these symmetries of these tensor networks can be completely understood, at least in 2 dimensions, in terms of bimodule categories. Bimodule categories, this is a very exotic kind of feature or topic of study in mathematics.
Frank, I would say that maybe some 30 seconds, and I think we should leave some space for questions.
That's very good. So anyway, so there's these bimodal categories that allow you now to construct all these examples, all these frustrated systems by starting from some very abstract algebraic equations. So you solve some algebraic equations satisfying somehow these rules. And from this, you can actually construct all the possible critical models that people kind of care about. And this basically implements somehow this Baxterization program of Vogel-Jones that won the Fields Medal, that tries to connect basically critical long-range behavior with topological features. So topological field theory with critical formal field theory. And this is exactly somehow the central kind of topic that people in physics are interested in. So it turns out these tensor categories kind of combine many different kind of ways of looking at this. And the tensor networks are exactly kind of implementing or providing the representation theory for these very abstract kind of notions. Okay, so this is an example of the three-state Potts model that kind of I alluded to in the beginning, how to kind of understand this and what are these symmetries. It turns out that there's 8 non-trivial of matrix product operator symmetries for the Potts model. You construct them using these methods. You can kind of construct all these tables, the conformal towers. Actually, a paper that we post today is about exactly a critical lattice model for a conformal field theory that was kind of conjectured not to exist. Well, we show using this kind of construction that it exists. This paper will come on the archive tomorrow. And this is my last slide, in which I would like to thank all my students and previous students actually that worked on exactly this program. And especially somehow Robin van Hove and Laurens Lotens are really pushing this whole program of understanding somehow these non-local symmetries and this emerging behavior in terms of somehow these tensor networks. And also Bram van Ecke and Laurens van Verstraete are certainly the 2 people that pushed very much these numerical kind of methods that I started talking about in the beginning of my talk. And so I think I have to really stop here. So thanks for your attention.
Oh, thank you very much, Frank, for this wonderful talk. It's really fascinating, and it was great to see all these connections between MPO structures and this topic. And there is some 2.5 minutes for some questions, and please raise your hand, or just put it in the chat.
Yeah, I already raised my hand. Yes. So.
Mm-hmm. Yeah, please go ahead.
Yeah. Thank you so much for this interesting talk. I would like to go back to the ice problem. If we examine the phase diagram for water, look at the pressure as a function of temperature, I think if I remember correctly, we have like 12 different phases. But when you zoom in on the 0 temperature, 0 Kelvin, people wrote question mark and said nobody knows exactly what is the phase close to 0 temperature. Can you comment on this problem?
Well, this is well. It turns out that I'm not so sure how many phases, but there's certainly at least.
I think around 12. Around 12, I think.
Indeed, but so in this particular case, we only focused on 2 different cases: the diamond ice and hexagonal ice. 1H I see here. This is, I don't remember exactly what that means, but certainly we solved that problem, and we really were able to calculate somehow the residual entropies there up to like many digits of precision.
No, I thought once you zoom to 0 temperature where you have a quantum, supposed to have a quantum phase, I thought maybe like your approach can give us like a more insight. Why this is so complicated?
No, this is a very good point. So basically these are the ice rules. So you really kind of try to, so what at 0 temperature, you basically define your Hilbert space as being all the configurations that satisfy the ice rule. And here you calculate basically the dimension of that Hilbert space. That's what this entropy does. Of course, at 0 temperature, there will be now other effects that come into play, and you will have an effective quantum Hamiltonian that is now defined on that Hilbert space that does not have a tensor product structure. And I have not talked about this, but this is extremely interesting indeed. Now to do physics actually projected on that non-local Hilbert space. Because there's no tensor product structure anymore, because actually everything is connected to each other. And this is certainly an area of this is an extremely interesting area of research. What happens now at zero temperature or very low temperature, if you kind of have something like a Heisenberg antiferromagnetic, but additionally on the Hilbert space of all spins that satisfy this ice rule. And indeed, so we have certainly not pushed that, but these methods that I'm talking about here would exactly be the kind of things that we need to do to get there.
Just like
Okay.
one quick
I'm
question.
sorry. I think we have. I'm sorry. I have. Please. I would like to ask also Christian that if you could ask your questions personally, because I mean we have to change and then ask Ignacio to present his talk. Otherwise, we will be just delaying the schedule. So, is it okay that we leave the discussions for some private channel? And so therefore, I would like to announce that the next speaker is going to be Ignacio Cirac from the Max Planck